And with this one, again, if we look at the resistance of conductors, we have rho times length divided by area. And so because it's aluminum, we can't go with ohms per 1,000 feet column. So we're looking at this formula, and we have feet. So again, remember now from the table for the properties of common conducting materials, we had 17.0 ohms times circular mils per feet for aluminum. And we're going to multiply that by 1,500 feet. And now we need an area. Okay, so go to the American wire gauge and find the area of number 8. And it don't matter what kind of material it is, the area is defined by AWG number 8. And that is 16,509 circular mils. Okay, so our unit comparison or conversion here tells us that circular mils cancels with circular mils, feet here cancels with feet here, and we're left with ohms. Okay, that's good because we're calculating resistance. So now resistance is 17.0 times 1,500 divided by 16,509, and that gives us 1.545. So I didn't round that to 1.55. I'll keep four significant figures, and our unit is ohms. Okay, so remember that because rho here is defined for 20 degrees, then that is at plus 20 degrees C. So now we want to say then that RT1 is the resistance at 20, and that is 1.545 ohms. And that means then that T1 is 20 degrees C. And so we're going to say that RT2 is R at negative 20. And of course, that is the unknown here. And that makes T2 equal to negative 20. Now, we could have equally well called them the other way around, but, you know, for regards of setting up our ratio, that's what we want. Okay, so the ratio says that RT1 over RT2 is equal to 1 plus alpha 0 times T1 over 1 plus alpha 0 times T2. And we need alpha 0, which is the temperature coefficient of aluminum. And we need to get that from the table, again, of properties of common conducting materials. And if we do that, we find that it is 0.00424. Okay, so we're going to solve this now for RT2. So RT2 is equal to, by cross multiplication, right, we have RT1 times the expression on the bottom of the right side, 1 plus alpha 0 times T2. So it's very important for T1, T2 on the top. So then 1 plus of 0 times T1 on the bottom. And so now we have then 1.545 degrees multiplied by 1 plus 0.00424 times negative 20 degrees over 1 plus 0.00424 times plus 20 degrees. Now, you know, I don't know how many sets of brackets you want us to put in here, but the biggest mistake that we see in this section is that you'll do 1.00424 times 20, and that's not correct. The multiplication must be done here before you add the 1. Okay, so add the 1 after. And so that becomes now 1.545 multiplied by 1 plus, multiply these two numbers together. And 0.00424 times negative 20 then actually gives us a negative number, negative 0.0848. So in the denominator, 1 plus positive 0.0848, because we got the same expression down there, right? 0.00424 times 20. Okay, so now add the 1. So we got 1.545, and on the top we actually have 1 minus 0.0848, so that gives us 0.9152. And on the bottom, we got 1.0848. Again, it's very important to get the algebra correct here. Now, once we do that, you know, you'll notice that the numerator got a 0.91, the denominator got a 1.0848. And so the idea is that that's going to represent a drop in resistance. Well, the temperature went from 20 to negative 20, and so we expect a drop in resistance, right? And so now RT2 is equal to 1.545 multiplied by that ratio, and 0.9152 divided by 1.0848 is equal to 0.84366 basically. And so, you know, that's a drop of nearly 16%, 15.5% basically, right? And RT2 now comes out to be 1.3 ohms. And so if I round it to 3 significant digits, 1.30 ohms. And it's actually 1.303 if I want to keep the 4 significant digits over there. Okay, so remember now that that RT2 is at negative 20 degrees C.